Hello, my name is Michelle Effros, and I work at Caltech, the California Institute of Technology in Pasadena, California. I went to Stanford University. I was there both undergraduate and graduate. Information theory is just a beautiful field where there are beautiful answers to really important real-world questions. It is the mathematics behind communications. It explains what is and is not possible in a communication system. And so information theory answers the question, is it possible to communicate reliably? And if so, how much information can I reliably transmit through a particular system? So one of the big challenges in information theory is that the problems that have been solved to date have mostly been very small. What we're trying to do is figure out how to get information theory to expand and answer questions about very, very large networks. Networks with millions or billions of individual communicators. Whether it's the internet or your cell phone, you're communicating over a very, very large network all the time. Most of these networks don't work anywhere near as well as they could. And so we have to push their capabilities to the limits. And so understanding where those limits are, what is and isn't possible over those networks, becomes increasingly important. It turns out that operating individual channels at their own individual capacities is in general not the best thing that you can do in a larger network. In many cases, actually, you can get much more information through than the individual capacities of channels suggest. So we're proving that it's possible to build computational devices that will find the capacities of networks, will allow you to plug your network design in and compare its performance to another network design, for example. I think it's an important new tool. It will be useful both for studying traditional communication networks, design networks, as well as maybe natural communication networks. So you can use the same ideas to understand communication in biology among cells or among neurons and so on. One of the intriguing questions that I've been working on recently sounds very simple. So you imagine that you have a network. It's made up of a collection of edges. You can think of these as wires or other communication links by which any individual node can talk to any of its neighboring nodes in some network. So we ask the question, what is the capacity of the network with the edge, and how much can that capacity change if I remove that single edge from the network? For example, after a large earthquake or other kind of disaster where the phone system is down, you might want to have everybody's phones help each other to allow communications to occur even when the base stations themselves, the wireless system, is down. And it turns out that in wireless networks, the benefit of cooperation is far bigger than the cost. That is, the extra amount of rate that you spend for them to sort of share a little bit of information allows you to send far more information through the network as a whole than would be predicted by just how much information they're actually sharing. What's exciting for me right now about information theory is the combination of the field, the coming together with other fields that will help us study not only much bigger networks, but also a really broad variety of different kinds of networks. We'll start to be able to use the tools that were developed to instead understand other kinds of communication systems, such as biological communication systems. So your DNA is a form of communicating information from one generation to the next. Likewise, cells communicate. I've come up through information theory with a great group of women, and that's been a really positive thing for me. WITHITS has provided a great environment where women can meet each other, can just get to know each other, can share stories and make new friendships and sort of just find each other in thinking about how one finds one's way through academia or through industry, through their path, while staying active in this field. There are still so many traditional ideas as to who does which job. I think that those ideas get passed down from generation to generation, that people don't necessarily raise their little girls to become engineers. They don't necessarily even expose them to what engineering is. And therefore, I think that many girls are surprised to even hear that, oh, this is a possibility. It never occurs to them. I was one of those girls. It never occurred to me that engineering might be a good idea for me. And engineering is enormously creative. It is all about creating something, right? You're solving a puzzle, you're often building something, you're really in the process of creation. And information theory in particular is a beautiful area. It's an area where you ask really, really hard questions and get remarkably simple answers. The biggest thing in terms of choosing an area that I would tell people is find something you're passionate about. Find something that you really love, that you really enjoy doing, that you want to wake up every morning and spend your time on. Information theory is a way to learn how to predict the future. And if you can understand what will happen in a long sequence of random or unpredictable events, you have a lot of power, not only for communicating where those random events may be individual coin tosses or bit flips, but in the stock market and all kinds of different walks of life. These tools are very powerful.